Hello, I'm Maddie Basil, a current sophomore at Swarthmore College, and today I'm excited to be sharing with you a brief summary of the work that I and my research partner, Salma Hook from Reed College, completed this summer as part of our involvement in the summer 2019 Forestry Data Science Research Group. We had the privilege of working closely with research statisticians from the U.S. Forestry Service and in particular from the FIA, or the Forest Inventory and Analysis Program. Our research group collaborated primarily with the Interior Western FIA unit, and the project that Salma and I worked on was called the LANDFIRE project and was centered on exploratory data analysis and the reclassification of data products collected by the USGS LANDFIRE program. In particular, we focused on LANDFIRE's existing vegetation type variable, or EVT variable, which was used to categorize various plant communities. This EVT variable had the potential to usefully supplement FIA field data, but because it encompassed over 600 different classes, it was very inconvenient for FIA to take into account when they were building their estimators. We aimed to collapse the hundreds of distinct classes, some of which are shown in the table here, just so that you can get an idea of the specificity that we're dealing with when it comes to these classes. Our goal was to condense the current groups based on 4 important forest attributes: the volume of sawlog portion of vegetation, the above-ground biomass, the tree count, and the basal area, a measurement of the area occupied by tree stems. The k-means algorithm, which is shown in this diagram here, was our central methodology for breaking up the EVT variable into more practical classes. I'm not going to discuss the algorithm in immense depth because of limited time, but the process works by randomly picking k points from within your data cloud and then iteratively finding and repositioning centroids based on a distance measure. The important takeaway is that the final results are your observations ending up in groupings that are internally similar but dissimilar to other clusters. For each of the EVT classes observed in the interior west, we determined the average values of those 4 response variables that I mentioned earlier. Then we ran k-means clustering on the data. We also manually created a 0 cluster to house the particular EVT classes, which displayed average values of 0 for all 4 responses of interest. This methodology allowed us to formulate a new EVT classification system with only 5 distinct groups. The graphs here depict our more collapsed scheme, where k equals 5. And show each original EVT classification charted against 2 of our response variables of interest. As you can see, there are 4 k-means created clusters, as well as our additional 0 cluster, which is denoted by the dark blue point at the origin of both of these graphs. We developed preliminary names for each cluster based on the qualities of the vegetation groups that fell within that cluster. We have the shrub and scrub cluster 1, the pinyon juniper-esque trees in cluster 2, the small evergreen-like trees in cluster 3, and the larger evergreen-like trees in cluster 4. This table also captures additional information about each of the clusters in our k equals 5 scheme, including a more in-depth cluster identification, and in the rightmost column, a list of some of the most common former EVT classes which now find a home inside our new groupings. We also opted to create a scheme with 10 separate clusters, or where k equals 10. We can see here the 9 color-coded k-means created clusters, and then the dark blue dot representing the 0 cluster at the origin once more. The benefit of having this slightly less collapsed scheme lies in its ability to draw out more subtle distinctions between the EVT classes, especially with classes that displayed higher average tree counts and lower average volumes, which are enclosed within the red circle on the graph. With the k equals 5 scheme, the majority of data points in this area of the graph were binned into only 1 cluster, and now we can see them sifted out into 3 clusters. If FIA researchers determined that they wanted this patterning to be accounted for when incorporating EVT into their estimation process, our k equals 10 scheme could be appealing in such a situation. Shown here is the identification table that provides a little bit more information about the k equals 10 scheme. We can see the cluster descriptions, as well as the most common former EVT classes within each of the new clusters. One of the biggest difficulties that Salma and I faced when refining our cluster schemes was making sure that we not only generated groups that were homogeneous in terms of our 4 responses of interest, but also groups that made ecological sense. That is to say, we didn't want to just rely on the k-means computation that the computer spit out, but instead we wanted to make sure that the items clustered together were categorized in an intuitive way, which is the reasoning behind our manual creation of a zero cluster and our altering of k to highlight more subtle data patterns. Our result, as I've shown you, are two new collapsed EVT variables, one composed of 5 classes and one composed of 10 classes. Our hope is that working with a categorical variable that has 10 classes or less instead of hundreds of classes will allow FIA to use the EVT variable to strengthen their forestry-related predictions. Shown here are some of the previous works we referenced during our research. I want to extend my thanks to the team who put together EUSR for allowing me this wonderful platform to share my work, as well as extending my thanks to everyone attending for listening.